Hello and welcome back to Calculus 1, section 4.7 on L'Hopital's rule, which in all honesty is actually Bernoulli's rule, which L'Hopital paid for. It's interesting. L'Hopital was this rich guy who loved learning mathematics, and in the good old times, right, 200-300 years ago, the only way you can learn calculus and math was if you have a private tutor who's technically really good at it. So Bernoulli was the tutor, and Bernoulli is one of the iconic people in mathematics, responsible for a lot of things with probability, differential equations, statistics, and a whole bunch of stuff. I mean, Bernoulli distribution, Bernoulli equation, Bernoulli this, Bernoulli that. So one of his, lesser important results at that time was what we are going to learn today. Now, being that he never published it anywhere, and his paying student, L'Hopital, was the first one to publish this result, everyone thought that it was L'Hopital's rule, until it was later sorted in history that it wasn't. But it stayed, to be a L'Hopital rule because L'Hopital was the first person ever to write a calculus textbook. And that's where the people saw this result for the first time. So the first ever calculus textbook written was by L'Hopital. And again, he was the guy who just learned a lot of calculus and enjoyed calculus and all of that stuff. So that's how this ended up being a L'Hopital rule. Now, what is this rule all about? Well, it's a rule which states that if you have indeterminate form, there is equivalency between the results of two limits. Now, here we go. So if we have 0 over 0 or infinity over infinity, indeterminate forms, then limit of f of x divided by g of x as x goes to blah is equal to, by L'Hopital rule, the limit x goes to a of f prime of x divided by g prime of x. Obviously provided or given that g is different than 0 or g prime is different than 0, because we can't divide by 0. So this is the rule. Now, this is not your regular equal sign when you say 3 is equal to 3, x equals to x, or x equals to 3 when you know that the variable x is 3. That's not that. Because you cannot claim that this is equal to that, because we know that you have to use the quotient rule, right? Not two separate derivatives. What is equal here is the answer that you get for this limit and the answer that you get for the other limit. So that's what's equal. So this is giving you L, and that is equal to the L that you would get here. So the problems are not going to look the same. The functions are not going to be the same, but the outcome of the calculation of both of those limits is going to be the same, and that's what it's called, right, L'Hopital's rule. So with clearing that up, we can immediately practice this on the problem which I promised in the past that I will do first, because I did ask you at one point in chapter 3 to just trust me on the fact that the limit as x goes to 0 of sine x over x is equal to 1. I asked you to trust me on this, and I said, wait for chapter 4 and I will show you, right? Well, we are at that lesson. So now a limit of sine x over x is equal to what? Well, we know that the first method of solving limits from chapter 2 is plug x equals 0. And if you don't have vertical asymptote, 0 in denominator, and anything crazy going on, whatever the answer is your answer. If you get 0 in denominator, then you have to do whatever magic you must do. Well, in this case, when you plug in 0, you get what we call this indeterminate form of 0 over 0, which is what is required for us to run the formula below. So now, when I have 0 over 0 indeterminate form, I know that I can put this L'H, stands for L'Hopital, on this equal sign, and I can take two independent derivatives of the two functions I see. And that obviously will be cosine x and 1. Derivative of sine is cosine, derivative of x is 1. And now, guaranteed by the theorem above is that the result of this problem and the result of this problem is the same result. Right? You get the same value. But clearly the problem on the right is a joke to solve, because once you plug in 0 for cosine, you get 1 over 1, which is equal to 1. Therefore, our problem is equal to 1. So L'Hopital rule is going to be used only in cases when you have what we call indeterminate form, 0 over 0 or infinity over infinity. And if you have that condition satisfied, you are welcome to take independent derivatives, top from the bottom, denominator and numerator, right? Separately, not a quotient rule, separate derivatives, and then the result of that will be the same as the result of the original problem. Again, one more time, you have to first have the condition straight. Let me give you another example that you all know from chapter 2. Let's say 3x squared minus 6 divided by 4x squared plus 12x minus 1. We know that we can either use the front coefficients, right? Use the front coefficients. That was what we learned all the way back in pre-calculus. So the answer is 3/4 because both of these are x squared and x squared. So we know that the answer is 3/4. Then we learned in Calculus 1 in chapter 3 that we can divide everywhere by x squared. And then when we do that arithmetic, it works out to be 3/4 again. But now, when I plug in the infinity, I get infinity divided by infinity. Ooh, that's the indeterminate form, which immediately means derivatives. So we put L'Hopital on top of the equal sign, signifying that we are changing the problem, but this new problem will have the same answer. Now, when you take all these derivatives, you get 6x divided by 8x plus 12. And you arrived at the completely new problem. So if there was, nothing else on the page, literally nothing else on a page, just this one problem, you would treat this as a completely new problem. And you would just say, okay, I'm plugging in infinity, and you get infinity over infinity again, which means hit it by L'Hopital again. And what you get is just 6 over 8, which is 3/4. Got it. Now, in this particular case, right, in this particular example, I used L'Hopital twice. L'Hopital's rule. I used it twice. Every problem, every step, it's like independent problem. And if the situation allows you to, go ahead, do 10 L'Hopital rules, right, in a row. So the goal here, right, is to take the L'Hopital rule as many times until you get to the place where you can't take L'Hopital's rule anymore, right? Because there is nowhere to plug infinity to get infinity over infinity or 0 over 0 or whatever. So your job, your life or whatever is to use these right, 0, 0 situation or infinity over infinity, which we call indeterminate forms, in conjunction with those derivatives to change the problem into hopefully something easier, and then take the limit of the easier problem under guarantees that the answer will be the same as what you had before. So let's take a look at another example. I think I put this one on the exam at one point. It turned out to be a disaster, so I'm just going to use this one in class. So ln x minus 1 divided by x minus e. I was like, yeah, this is obvious. This is a joke. And then it was actually a massacre. Because I can't judge what's easy, what's hard. Everything is joke to me. So, you know, I need someone, I need a proofreader for exams. It's like, okay, yeah, students can understand this. Let's go with that example. Because I really thought that this is absolute joke of a problem. When you plug in e, ln of e is 1. So you're getting 0 on top. When you plug in e in the x in denominator, e minus e is 0. So it's 0 over 0, which means that you can take L'Hopital. Okay, so now when I take the derivatives, the derivative of ln x is 1 over x, and the derivative in the denominator is 1. So the answer is 1 over e, and that's it. Just walk away. Because there is nothing else that you can do here. I mean, when you divide 1 over x by 1, you get 1 over x. So that doesn't change. And we just go and get that. Let's take a look at another problem. Maybe something with trig or inverse. Ooh, inverse trig. Look at that. That's a beautiful problem. Limit x goes to 1 of 4 inverse tangent of x, everything minus pi, divided by x minus 1. Okay. So inverse tangent of 1 is pi over 4. Now, you might ask, well, how do you know that? And before you call witchcraft or something, I know that the tangent of pi over 4 is 1. Now, I know that because tangent is sine of pi over 4 divided by cosine of pi over 4. And I know that each one of these is root 2 over 2, which when you divide the same values, you get 1. So no matter which way you look at this, you will always get that the inverse tangent of 1 is pi over 4. So now what you get is that pi over 4, and you have the times 4 in the front. Well, that's going to cancel the 4, and you just have pi minus pi, which gives you 0. Now bottom is 1 minus 1, that's 0. So that's an easy one. Okay, I have 0 over 0, which means hit this with L'Hopital. Now we take our derivatives. 4 times 1 over 1 plus x squared, derivative of pi is just 0, and the derivative on the bottom is 1. Now we simplify this. I mean, divide by 1 and multiply by 4 is just like whatever. That's what we have. And now when you plug in 1, your answer is 2. Because 1 squared is 1, 1 plus 1 is 2, 4 divided by 2 is 2. And there you go. The limit for the problem with the inverse tangent up there is, as x goes to 1, is 2. This is an amazing problem for situations when someone says, what do you know? You're dumb or something. Pull this problem out, ask them what they know, right? See if they can get 2 at the end. So I hope you understand L'Hopital's rule. Right? That's it. I hope you're not disappointed. You must have 0 over 0 or infinity over infinity in order for this rule to work. Now, as you are all sensing, we're not done, right? Because, we didn't do much. We didn't do much. And I promised a long session. Well, see, these are the only 2 cases when you get to do L'Hopital's rule. When you have 0 divided by 0 and when you have infinity divided by infinity. However, we have all of these other forms that can be converted into 0 over 0 or infinity times infinity. And those are 0 times infinity, infinity minus infinity, then 1 raised to infinity, 0 raised to 0. Oh, that's going to be beautiful when you go 0 raised to 0 equals 2/3. And you go like, what? But yeah. And then infinity raised to 0. It's like, wow, infinity raised to anything is infinity. And then anything raised to 0 is 1. It's like, which one is it? And then the answer is like 3/4. So, yeah. Now we're getting into that weird, right, calculus realm where you get to say, oh, 0 times infinity is 2/3. Interesting. Let's see how that works. So we start by understanding, well, so let's call this 0 times infinity case. Right, that's our title. We'll have a special titles for all, well, not for all of them. The first one, the second one, and all 3 of these go together because the method of solving is the same. It's the exponential form, right? All right, so we have to go through these 3 cases. The first one being 0 times infinity. All right, cool. So we have 2 prerequisites that we need to remember or relearn or whatever before we can actually do these cases. So the first one is this notion from all the way back chapter 2, where we said that the limit when x goes to infinity of 1 over x is equal to 0. So you see that if you take 1 and you divide it infinitely many times, you get a 0 answer. Now that should make sense because if I take something and I cut it in half, what I have left is smaller than when I started. Then when I cut it in a quarter, right, cut the half that I have left in half again, which is actually quarter from the original one, right, you have even smaller piece. And that's me just cutting it by 4, right? Then cut by 8, cut by 16, cut by 32, cut by 64. So this little piece over here is 1 over 64 of the whole piece that we had to begin with. So you see that your 1 is much bigger than 1 over 64, right? It's 64 times bigger. So the more you cut in the denominator, the smaller of a physical piece you get to keep in your hand. Now, when you cut something with infinity, you have nothing to hold on because it's just gone, right? You cut it infinitely many times. So, right, that's why Joker kills the bus driver, right? Because less people to split dilute at the end, right? Bigger the cut. So this is the idea that, and then it goes the other way too. If the limit x goes to 0 of 1 over x, we know by infinity, by the vertical asymptote, right, it will give us positive or negative infinity depending on which side you approach. If you recall, the graph was like this, right? So if you approach from the left, it's a minus infinity. If you approach 0 from the right, it's positive infinity. We don't care which one we get. We just care that, you know, the input of 0 into this 1 over x situation is flipping 0 into infinity, or it's flipping infinity into a 0. So you are able to flip 0 into infinity or infinity into a 0, but you are required to have a division there. So when you take this rule that you should know from chapter 2 and add to it some algebra, and that algebra is that you can write your function as 1 divided by 1 over function, you immediately see how your 0 times infinity can be rewritten into infinity over infinity in one shot. Because if I write this 0 as 1 over 0 times infinity, didn't we just learn that 1 over 0 is infinity? Right? So the whole thing becomes infinity over 1 over 0, which is infinity over infinity, and it's indeterminate form. Like, I know that mathematical notation over here is absolute garbage, and I am not doing it a justice, but the hope is that you see how this simple algebraic manipulation, coupled with those two limits that we know from before, actually turn the situation of 0 times infinity into infinity over infinity. If you apply the same rule to infinity, it will turn into a 0, and you'll have 0 over 0 in that case. But the best, obviously, place to see this is in the example, right? So this is what you need. And now when you take a look at the example, hopefully it will make sense on how it's used. So let's go and get a 0 times infinity case from homework. I'm still expecting you to read the ones that are in the book. Let's go with, I need 0 times infinity. 0 times infinity. Okay, these are the trig ones. Can we get a non-trig one? It's kind of hard to find. This is they did not separate any of these problems. They just dumped everything on a pile and said, here, go. Right? So yeah, good luck learning this way. Yeah, there's literally nothing other than these trig examples. Well, I guess we'll live with the trig example. I know many of you love trig anyway. Yes, that was sarcasm at its finest. So, limit x goes to 0 of x times cosecant x. Okay. Fair, whatever. Now, let's take a look at the cosecant graph and decide what's happening at 0. So if you want to graph a cosecant graph, you will graph a sine graph. And then wherever sine hits 0, you will put your vertical asymptotes, because cosecant x is 1 over sine x. So if sine x is hitting a 0, right, that means 1 divided by 0, which is a vertical asymptote. And then all you need to do is to invert these cups like this, then get rid of the sine graph, and you have your cosecant graph. So this is your cosecant graph. It looks like this. And now, should I say obviously, as you are approaching 0, your y value goes to positive infinity. So this puppy here is 0 when you plug in 0, and a cosecant is going to go to infinity when you plug in 0. So this is the form 0 times infinity. It's not indeterminate form, which means we have to massage it with algebra to get it into the form we need. So your job is to pick one of the two functions and flip that using this algebra rule of 1 over 1 over f. So if you pick your x to be that function, then you get to write 1 over x times cosecant x, which you can actually write as cosecant x divided by 1 over x. So I did not use any L'Hopital rule or calculus or anything. I just did the algebra rewrite. That's all I did. And now when you check, the top is still infinity, right? Because it's the same function as cosecant as before. But look at the bottom now, right? As you plug in 0 for x, you get 1 over 0, and that goes to infinity. So the bottom is now infinity. And you have infinity over infinity case, which is indeterminate form, which means you can use L'Hopital. Now, using L'Hopital in this case means that you are going to, let's go limit, x goes to 0. You are going to take independent derivatives of top and the bottom. Okay, the derivative on top is a negative cosecant x cotangent x, hello chapter 3, and the bottom is negative 1 over x squared. Yeah, I just made this worse, right? The problem just turned worse because I still have the same situation, and if I keep doing the L'Hopital's rule, I'm going to keep getting the product rules and making the problem worse. So what happens when you make the problem worse? You immediately abandon it and flip the other function. Because when we flipped x, right? When we flipped x, it didn't help. It made the problem worse. So I'm going to just cross this out with, let's say, orange. There we go. I'm going to go back to my original problem, and I'll say limit x goes to 0 of x times 1 over cosecant x. Now, we can simplify this simply by saying x over sine x, because this x will multiply the 1, so that's your x on top, and then 1 over cosecant is your sine in the denominator. So now that I have that, and I plug in my 0, I get 0 over 0. Yay! Which means, hit it with the L'Hopital, limit, x goes to 0, and we have 1 over cosine x, which gives us 1, just like in that first problem we did. And now we know that the limit of x times cosecant x is equal to 1. Essentially, in this problem, 0 times infinity equals 1. Now, the answer at the end depends on the functions inside. Right? So it's not that every time you see 0 times infinity, answer is 1. Hell no. Right? The book example is having what? Example in a book that you can read on page 305 has answers 1/4. Right? So what is going to come out at the end is governed by functions and calculation. But this problem is very important and very good because, right, we tried to kind of cheap out and go with the flipping the x, and we saw that gave us worse problem than what we started with, right? Because this problem here is still infinity over infinity, but if you are to take another L'Hopital, right, which is independent derivatives of numerator and denominator, your product rule on top will just create a living nightmare, and the denominator is just going to go to positive 1 over x cubed. So nothing is getting resolved, right? Everything is getting more complicated and longer, and right. So if you are solving these problems and you see that you are getting, like the problems are getting worse and worse, instead of forcing it, try switching the other function. And that's what we did here. We took the cosecant and wrote it as 1 over cosecant. And then we just use the identity, right? 1 over cosecant x is sine x, which solved this problem in literally one step later. All right, so that is the situation when you have 0 times infinity. Now, we are going to see this a lot, especially in this next case. Infinity minus infinity. Ooh. All right. Lock the doors. No one is leaving. Infinity minus infinity. Remember, your job is to go all the way to 0 over 0 or infinity over infinity. That's your goal, so you can use L'Hopital's rule. We achieved that goal in a previous case by using this algebraic trick here, and we see that my 0 times infinity turned into a 0 over 0, and I was able to use L'Hopital. So the question now is, how do I go from infinity over infinity or all the way into one of these two? You're essentially asking, how do I go from subtraction all the way into division? And the answer to that is factoring, and then also the previous step of 1 over f. So those will be used now to transform infinity minus infinity case into these cases that we can easily solve using derivatives. Okay. We do have a problem given in the book, and I kind of want to do a different example because the one in the book you can just read. So let's see. Well, yeah, let's do a similar example to the one given there, and then we'll figure out. So again, read the one that is given in the book. Let's go with problem 64, and then we'll do another one for a good measure. So limit x goes to infinity of x minus square root of x squared plus 4x. So x minus square root of x squared plus 4x. So this is what we have. Now, when you do this, substitution, which is infinity, you get square root of infinity, that's still infinity. So you do have infinity minus infinity. So that's our case. Now, to transform this into division, I have to go through multiplication, and multiplication is simply obtained here by factoring, because factoring will give you everything. So let's go. I need to factor out x, but I don't have an x here to to factor it. So I need to get that x. Now to get that x there, I need to factor x squared in here, inside the root. So we start by, we have to copy this limit every time. We start by first factoring x squared inside the parenthesis. And then that x squared is going to escape as a single x outside, and then we'll be able to factor out x. So we factor out x squared because we know what we need, right? We need the x in front of the root, which means we need x squared in the root, so it can come out as a single x. So limit x goes to infinity, and then we have x minus x square root of 1 plus 4 over x. And there we go. Factor out x now, and what you have is, when you factor out x, what you left is with 1 minus the square root of 1 plus 4 over x. At this point, I should welcome you to calculus and ask you, how's your algebra? Right? Because if your algebra is not on par with this stuff, it ain't gonna be pretty in Calc 2, for the most part. Over here, what? You're gonna miss one problem on the exam 3, and you're still gonna say, yeah, I don't care. But let's see what happens in Calc 2. So every single step you guys see here is an algebra step. We were set on getting the multiplication because now when I plug in infinity, what I have is infinity times 0, and I know how to deal with infinity times 0. Now, why is the parenthesis 0? Well, when you plug in infinity here, 4 over infinity is 0, and then all you have is 1 minus 1. So 0, right? Now we use 1 over f to switch this into 0 over 0, and we can finally use L'Hopital. So limit x goes to infinity, like each one of these is equal, right? And now I have my 1 minus square root of 1 plus 4 over x, and the bottom is just 1 over x. Remember, that's the one that I want to push down, so x becomes 1 over x by the rule above. All right, now I have 0 over 0, and we can bring in the heavy artillery, right? L'Hopital, Bernoulli, whatever. Take independent derivatives. Now, denominator is easy. I hope you will memorize this one, so you know you're not wasting 20 minutes working a quotient rule on it. Just do yourself a favor in life, right, and memorize it, because you are gonna see it like 5,000 times. So the bottom is easy. It's just some shortcut that you memorized. The top derivative of 1 is 0. We have this negative. Ooh, the derivative of square root. Well, we know what that is. It's 1 over 2 times the same square root. And then times the derivative of the inside. Times the derivative of the inside. So what's the derivative of 1 plus 4 over x? It's negative 4 over x squared. It's this derivative all over again, which is just times 4. So times negative 4 over x squared. That's the chain rule. Why do we have a chain rule for this derivative? Because it's not root x. It's root of some mess. And that mess will have times g prime, right? Which is the chain rule. And at this point, we can cancel and do a lot of stuff here. First thing is I'm going to cancel these two completely and just get a 4 on top, because when you divide -4 by -1, you get 4, and then x squared and x squared just cancel. So now this is the algebra step where we simplify everything, and you get -4 over 2 square root of 1 plus 4 over x. And now we cancel these two, and when you plug in infinity, this will go to 0. So you just have a 1 under there. The answer is -2. Yeah, who would say that infinity minus infinity is -2? It's not, right? It's in this case where the functions line up this way. The book did a similar example, and instead of having, we had plus 4x, I think book has -3x. Let me go see that. Yeah, the book has -3x there. And their answer is +3/2. Right? Yeah, +3/2. So there you have it. The answer at the end will depend on what functions and what numbers you have in the problem. All right, before I do another example of infinity minus infinity, I just want to quickly recap this procedure again, because this was literally 90% algebra and then 10% of derivatives and a limit to plug in infinity in one spot. All right, so let's go. We have infinity minus infinity case. That means that from subtraction, we need to go into division because we want one of the indeterminate forms. Now, to get there, we have to factor for multiplication. And then once we have that, we use the trick over here to change multiplication into division. Once we have division, hopefully, it's going to be indeterminate form, and then we can use L'Hopital. If it's not indeterminate form, so you're getting 0 divided by infinity, or you're getting some other nonsense, make sure you did your algebra correctly, number one. And number two, if you did everything correctly and you are 100% sure that you didn't make any mistakes and that's what you have, then yeah, you don't get to use L'Hopital's rule. Like, good luck with whatever else works. I mean, graph and chart always works for limits. But this only works if you have 0 over 0 and infinity over infinity. So, in order for us to eventually factor x, like we did here, we know we have to create that x. And that x is created by the x squared under the root that goes out and becomes x. So, we first factored out x squared, then we took x squared out, and once the x squared is out, which became x, then we factor that x. And that created 0 times infinity form. Then we flipped one of the functions, made it 0 out of 0, 0 divided by 0, I mean, and then go down the problem, right, where you took the derivatives and simplified, like more algebra on top of algebra you already had. All right, so let's see if we can find another problem that would be infinity minus infinity. Ah, great. This looks bad enough. 60. Limit x approaches 1 minus of x over x minus 1 minus x over ln x. Is this infinity minus infinity? So problem 60, x goes on, x, okay. Like I would like to be that, but, right? What do we have? We have 1 over 0 minus 1 over 0. That is infinity minus infinity. Remember, when you plug in 1 over here, you get 1 minus 1, and that's a 0. And we said that when you have 1 over 0, right, the answer is infinity in the limit. Every time, that's where the vertical asymptote is, and you know that the function follows asymptote up or function follows asymptote down. It's either one or the other. But nevertheless, whether you have a positive or negative infinity, we don't care. It's infinity. That vertical asymptote is a single line that stretches from negative infinity to positive infinity on the y scale. All right. So once we have that, right, established that this is infinity minus infinity, our next goal is to factor it to make multiplication, because that's our path to division. So when I factor this x out, I am left with 1 over x minus 1 minus 1 over ln x. And now, when I try to use the, when I plug in -1, what I come up with here is 1 times, and this is 1 over 0 again, so infinity minus infinity. So, it doesn't fit now, right? Because I have x, but that actually didn't fix anything inside the parenthesis. And I don't have 0 times infinity to do the trick with multiplication, right? So we're technically stuck in this position. So I factored x, right, hoping that would fix the story, but it didn't. So what other methods, right, or things can I use for this? Well, factoring is definitely one of them. But factoring didn't help because we got 1 times infinity minus infinity, so that's not what we were after. Okay, well, yeah, tough luck, but now the only thing that I can do here, other than obviously foiling and going back in original problem, is to just add these fractions. Like there's not, I mean, subtract fractions, whatever. There is not that much I can do. So let me see if that helps. So x times, and now I have ln x minus x plus 1 divided by x minus 1 times ln x. So this is subtract fractions. Because, you know, at this point we're desperate. Like there's nothing I could do other than trying this. So now, if I can somehow, you know, do something here, maybe it would work out. So let's see what we have. When I plug in 1, this thing goes to 1. Ln x goes to 0. And then I have this times this give me a 0. Okay. And when I plug in 1 on the bottom, I get this thing to give me a 0 and this thing to give me 0. Yes! The whole thing is 0 over 0. Now I do have this 1 in front, but that doesn't change because it will just multiply the top 0 and it would not change. So you can actually, if you want to, you can put that back in and make x ln x minus x, whatever. Okay. Oh, we can also invoke the rule. Now I can get rid of all of this red stuff. We can also invoke the rule on multiplication of limits, if you studied the rules at all, where you can make this separated from the limit of this. That's another cool thing that you can do. All right. So now I have 0 over 0 on this side. Obviously, this is just equal to 1, so who cares? So 1 times the limit x goes to 1 minus. And now we take our, oh, I forgot to put the L'Hopital here. And now we do these derivatives. So it's 1 over x minus 1 on top, and derivative of plus 1 is 0. On the bottom, we have a product rule. So copy the first times derivative of the second plus copy the second times derivative of the first. So this is 1 times limit is just limit. So x goes to 1 minus. And what I have here is 1 over x minus 1 divided by x minus 1 over x plus ln x. Now, if I plug in 1, I am still, right, not good because there is an ln x there. But the hope is that this is still 0 over 0. And it is. Because when you plug in 1, 1 over 1 is 1. 1 minus 1 is 0 for top. And on the bottom, you have 0 plus 0, also 0. So we can do another L'Hopital. X goes to 1 minus. Here is that derivative that you are going to see like 15,000 times in life. Now you have the quotient rule over here. And then it would be plus 1 over x, which is the derivative of ln x. So just do this quotient rule, which gives us the x squared. And it goes x times the derivative of top minus top times derivative of the bottom, which is 1. Okay. Gotta be good with derivatives and derivative rules. And not mix it up with a whole bunch of things. All right, so let's simplify. This is negative 1 over x squared. Now on the bottom I have x minus x is gone, so it's just 1 over x squared plus 1 over x. Right? Because the top works out to be x minus x plus 1 over x squared. These two guys cancel and just have 1 over x squared. Good. Multiply top and bottom by x squared because you can. And there you go. That's negative 1 divided by 1 plus x. So negative 1/2. What a cool problem. Took forever, but yeah. And hope is that you will go back and rewatch this like a couple of times until it all makes sense. Cool. That's infinity minus infinity. Factor, and then do the trick of 1 over 1 over f. And then, I mean, in that case, you should be getting the indeterminate form, and then what you do is you use L'Hopital rule, a little bit more algebra, and you're done. But it's a lot of algebra here. We are left with our exponential forms, right? I said you have 3 of them. 1 to infinity, 0 to 0, and infinity to 0 cases. And this is the last batch, but we still have one more concept to cover after the growth of functions, growth rate of functions, after we're done with this. All right, so all of these have the same way to solve them, which is, again, logarithmic, right, stuff. Now, we must start, otherwise the lecture is garbage, we must start with the most famous one. That's the one. So, first of all, your problems need to look exponential. So if you have, let's say, sine x raised to the tangent x, that's good, right? That's this form, because you have, one trig function as the base and the other one as the exponent. So this is okay of a problem. This is also okay. You have a base and you have an exponent. So it doesn't matter whether it's a trig functions, ln, e's, you can have anything there, right? Literally anything, but it has to be exponential, because all three cases up there are all exponential. 1 raised to infinity, 0 raised to 0, right? Infinity raised to 0. So we have to have that. Now we're going to check and see if the form we have matches one of the three cases. Because if it doesn't, then it's not this, and you have to move with something else. Okay, plug in infinity. 1 over infinity is 0. And then plug infinity for the x over there. You have 1 raised to infinity case. Right? This is going to go to 0. This becomes infinity, so 1 to infinity. All right. So now we know we have that. And the question is, how do we solve all of these cases, no matter which one of these you get? And yes, you guessed it, we are going to use ln procedure for it, just like logarithmic differentiation. So we're going to set our problem equal, leave some space, equal to y, and then we are going to ln both sides. So we're going to put ln on both sides. We have ln y is equal to, now there is a proof in mathematics which is given to show that you can interchange log and this. It's part of advanced calculus. Has to do with function being increasing and all of that kind of stuff. But we can interchange these. And, for the purposes of Calc1 course, you can always do that, okay? And unfortunately, right, because it's not the class for it, you don't have to give the proof of why you're allowed to do this. You can just say, divine entity told me to, which is me in this case. Okay, now why did we involve ln in a problem that didn't have ln? Well, ln has that property that can strip off these powers and put them in front as multiplication. In which case, right, we break this exponential in function, right? So ln y is equal to the limit x goes to infinity. We have x times ln of 1 plus 1 over x. There we go. So now, when you plug in your infinity, you get your infinity here, and you get your 0 there, because, right, 1 over x is going to be 0, so ln of 1 is 0. And we know when we have infinity times 0, we know that we have to use f equals 1 over f. That's what we learned as a necessary step, right, in solving these problems. So we're going to write this now as ln y equals to the limit x goes to infinity, and now we use that algebra witchcraft, ln 1 plus 1 over x, and this becomes 1 over x. in denominator. So when you plug in your infinity now, you get 0 over 0, which is indeterminate form, which in fact allows you to use L'Hopital's rule, or as I would say, L'Hopital's hammer, like Thor. Limit x goes to infinity. There we go. And now we take these independent derivatives. Now, as I always promised, right? You're going to see this over and over and over again. Just memorize it. And on the top, you have the ln. You have the ln derivative on top. So you know that you're supposed to put the function as is and then multiply it by the derivative of the bottom, which is actually the same. Right? You're taking the derivative of 1 over x, and that's just going to be negative 1 over x squared. Now, those cancel. They're gone. And you don't have much left. So you have your ln of y is equal to the limit x goes to infinity of 1 over 1 plus 1 over x. Now, when you plug infinity here, it's going to go to 0. So the whole thing is equal to just 1. Actually, I can write a step of 1 divided by 1, which is 1. There we go. So you got that your ln y is equal to 1. Now remember, y was your entire limit. And you just need to get rid of ln now, which obviously you get rid of by e both sides. And your y is equal to e to the 1, which is just e. That means that the limit as x goes to infinity of 1 plus 1 over x to the x is equal to e. Whoa! That is your calculus definition for that very special number, e. Now we know what e is. Yeah, it has decimals and blah, blah, blah. But there you have it, the definition for it. Now, this is going to show up a lot in Calc 2. So I hope you're going to know this one. There is going to be a chapter on it. Yeah, 2 sections, but still. And you are going to have this show up in chapter 10 a lot as well. And 11. So yeah, you kind of got to know this. Now I'm going to give you even more powerful formula to digest in free time. And that is 1 plus a over x raised to the bx is e to the ab. Now I will call this formula boss formula, because obviously when a and b are 1, you are going to get just e. But if you put a to be 3, then your answer is e cubed. If you put a to be 3 and b to be 4, then you have e to the 12 as your answer. So yeah, that's going to come up. So I hope you're going to remember it. All right. So what we had here...
Professor,
yes?
I have a question about that formula that you just wrote.
Uh-huh.
Wouldn't that mean that e would be e to infinity in the problem above?
Are you talking here?
Because you have... Oh, wait, never mind. Because...
Remember, x goes to infinity.
Yeah, not b.
Not a, not b. Okay, yeah, that's a good question, right? It's good to point that out now, so we don't have issues later. That's good, yes. So you always have to be careful what your limit goes to, right? And it's x goes to infinity, so your a and b are just what we would call parameters or numbers or something like that. So yeah, that's that. Cool. Now, let's do another example of these exponential things. I'm just going to pick something from homework. Something from homework. Let's see. Oh, well, 78 is sine raised to the tangent. Yeah, why not? I know you guys love. As x goes to 0. That's 78. Yeah, okay. Like, you love this stuff. It's trig. It's coming up in Calc 2. So, let's do more trig. All right. We know the drill. Y equals, leave some space, limit x goes to 0. You need to sneak in over here ln, so you leave some space. Limit of sine x raised to the tangent x, and then you snuggle in ln on both sides. The next step is the same as before. Put the limit in front. This is 0 plus because of the tangent you are approaching from the right. So, yeah. If you approach tangent from the left, you get negative infinity. But whatever. Interchange these. And then peel off that power. So that will be your basic pre-calculus. All of this was just a pre-calc situation. And if you are having a heart attack right here, I understand it. Because we are having a limit and then the tangent, and then we have the function composition of ln and sine. So yeah.
Heart attacks can be fun sometimes.
I guess. I don't know. This is, I mean, the way I look at this is like a puzzle that has blocks in it, and I can just, unwrap this and see what we get. But anyway, when I plug in 0 for tangent, I get 0 because tangent of 0 is 0. Why? Because the tangent graph goes through 0, 0. So input x 0 spits out output y 0. So that's that. Now sine also gives you 0 when you plug in 0, but it's ln of 0. And ln of 0, because it's a function composition, right? Ln of 0 is negative infinity. So this piece is negative infinity. Yeah, we don't have to worry about that sign. So it's 0 times infinity case, which means we gotta use 1 over f. So I hope that these graphs over here helped. As I plug in 0 in tangent, that's just a basic tangent graph. That's a 0. We are done with the first term. Now, when you plug in 0 in sine, you first will have to solve sine of 0 and then ln of the answer. So, sine of 0 is 0, and then you have ln 0 to worry about. Now, ln of 0 is negative infinity if you draw basic ln graph. So that's how we obtain that the whole problem here is 0 times infinity. And now we hit this with 1 over f. Now, if I end up flipping the wrong one, yeah, I'll just go back in a problem and fix it. I don't know which one I should flip. I'm just going to pick tangent now because it's cheap. But maybe I have to pick ln. I don't know, right? So I'm just going to go with the cheap one. And then if I get smacked in the face, I'm going to go back and change it. So ln sine x is going to stay on top, and 1 over tangent x is going to go on the bottom. Now, I know enough trig to know that 1 over tangent is, can anyone help me? Since I know so much.
Cotangent.
Very good. Cotangent x. Perfect. Okay, so now if you try your analysis, this is still going to be infinity, and this is infinity, so infinity over infinity. Now you might say, wait, hold on. How do you know that cotangent of 0 is infinity? Well, the cotangent is cosine divided by sine. That means sine on the bottom, when it's 0, I have vertical asymptotes. So here's my sine, and you see that you have a vertical asymptote at here and here and here and here, right? But your y-axis is a vertical asymptote. So if I am approaching 0, I'm approaching vertical asymptote, so the answer can only be one of the infinities. I don't care which infinity, I just know it's one of them. That's all I need to know. I don't care which one. So we got to the point where ln y is equal to the limit x goes to 0 plus, from the right, of ln sine x over cotangent x. And the verdict is infinity over infinity. Hit it with the L'Hopital. So here is the L'Hopital. Limit x goes to 0 plus, and now we have our derivatives. Ooh, it's ln. We all know what that means. When it's ln, you put the function as is on the bottom, and its derivative on top. Oops, derivative of sine is cosine. Now, the derivative of cotangent is cosecant squared x, negative cosecant squared x. Now, there are a few ways in which you can massage this trig here. I would turn this cosecant into -1 over sine squared x. Like that's the way that I want to go about, because I think it's the easiest way to see this. Now you can use Pythagorean identity and a whole bunch of other things, but when you have a cosine x over sine x, and you have -1 over sine squared x, and you multiply top and bottom by sine squared x, all of this simplifies very nicely. The top becomes sine x cosine x, and the bottom becomes -1. So, boom, 0. Because sine of 0 is 0 and cosine of 0 is 1, so 0 times 1 divided by -1. So the whole thing is 0. And there you go. When you raise sine to a tangent, right? Raise sine, tangent to a sine. When you raise tangent to a sine, and limit goes to 0, the answer is 0. We computed that stuff. We didn't make it up. Those are the cases, guys. So we had 0 over 0, infinity over infinity as the indeterminate form basic cases. And then we studied 0 times infinity, infinity minus infinity, and these exponential ones. Now, the last part of the lecture is the growth rate of functions, which will be expanded on in Calc 2, but for sequences. So you'll have more stuff added to the list that I bring in today. Growth rate of functions. Dare I say, part 1 to be continued in Calc 2. Why do we want to study this? Well, if you recall back in a good old pre-calculus days, you were memorizing horizontal asymptotes, and you memorized that if you have a bigger exponent on top, there is no horizontal asymptote. When you have the same exponents, you use the front coefficients, and we have the bigger exponent in the denominator, the answer is 0, right? Now, when you transferred those 3 rules into calculus, The bigger exponent in the numerator meant that the limit was infinity, so there was no line, there was no slope, because infinite, right, infinite slope. And then when the powers were the same, you had the front coefficients. And then when the denominator had the bigger power, the asymptote was at x-axis, which was 0, right? Y equals 0. So it transferred all the way through. Now, what does it mean for a function in the numerator to have a bigger exponent than the function in the denominator? So if you have, let's say, 3x squared minus 1 divided by 10x plus 6, right? Well, the growth over here is the x square growth. And the growth on the bottom one is a linear growth. You see that this one is growing much faster than this one. So it's going to win on the long run. And this is why you can call on the limit here as x goes to infinity to be infinity immediately, because the top is growing much faster than the bottom. The function in the numerator grows much faster than the function in denominator. It takes a very long time to say that, other than the top grows faster than the bottom, right? So in some sense, you say, oh, we can generalize this and say that now this is not a proper mathematical notation. This is our street talk, okay? You can say that the limit x goes to infinity must be infinity here. Doesn't work for 2. When the limit x goes to infinity and you have fast over slow, and we'll see what that means, the answer is infinity. And if you have the limit of slow over fast, the answer is 0. Also, x goes to infinity. So if we know which function grows slower, and which is the faster function, we don't even have to take the limit if you have this limit x goes to infinity, which is what you always have when you in Calc 2. 2 chapters of every single problem having a limit where your x goes to infinity. I mean, we use n over there. So it literally doesn't matter if I go to any of my Calc 2, right, and poke into anything on chapter 8. It doesn't matter which one I pick, right? Anyone in chapter 8, chapter 10. Any one of chapter 10 problems that I pick, right, it's going to have limit b goes to infinity. Chapter 10.5, limit n goes to infinity. Chapter 6, limit, I don't need to scroll. I just get to poke, and every single limit goes to infinity. So if you know these very helpful shortcuts, right, your Calc 2 life becomes a little bit nicer and easier. So, so what does it mean, slow and fast and growth rates and all of that stuff? Well, here we go. All we need to do is we are comparing the y values for function x, for function 2x, for function x squared, for function 2 to the x, and for what I call the boss function, x to the x. Now, prior to this, there is a square root of x, there is the ln x, and those are the slow ones, but they will show in the theorem. I just want to give you what does this mean, slow, fast, blah, blah, blah. So what are your x values? Well, they're 1, 2, 3, 4, 5, 6, going on to infinity. Just numbers 1, 2, 3, 4, 5. Now, 2x is a linear function. Well, x is linear as well, but 2x has twice the slope. So these values are 2, 4, 6, 8, 10, 12. So you see that they're growing. They're growing linearly, but on the 6th row, this has a value of 12. so it's growing faster. Now you can see that on a graph. Obviously, one is 45 degrees, the other one goes like that. So clearly this one is growing faster in time. If this is your time and this is your money, right? You want to pick this one because in shorter times gives you more money. That should be common sense. So definitely grows faster than the x one. Now all of the other ones will have the same behavior. X squared, go square them all. Well, 1 squared is 1, and then 2 squared is 4, and 3 squared is 9. Oops. 3 squared is 9. 4 squared is 16. 5 squared is 25, 36. So you see that x squared is the bigger boss than any one of these. Now we have heard of the exponential growth, right? Okay, 2 to the 1 is 2. 2 squared is 4, catching up. 2 cubed is 8. It's like, hey, we're losing. 2 to the 4 is 16, up, catching up. But then, boom, 32, 64, 128. Once the exponential function catches up, it just explodes. Remember what the graph for exponential function looks like. Lame, 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 boom! Right? Lame, and then boom. So it needs time, right? It needs time for it to catch up. And that you can see that, right, trying to catch up with x squared. See that the first 4 values, they are the same or lower than x squared, right? And then on the 5, absolutely destroying them on number 6, right? This is my favorite, like these 2 columns. I say this is your Intel and this is your AMD. Because right now, where they are, like AMD is kicking Intel. Well, Intel is down, curled up and crying. AMD is standing upright, literally kicking them on the floor. Like that's how much the AMD is wiping the floor with Intel now, with the lineup of processors. If you haven't seen the latest, and obviously I'm AMD fanboy, so I'm like gloating. Because, for years people were like, Intel, 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 Intel. And it's like, yeah, look it up right now. Same price point, double the performance in multi-threading. Anyway, then we get to the big boss. Ooh. 1 raised to the 1 is 1. 2 raised to the 2 is 4. Nothing to see there, right? Pretty much the same as everyone else. But then 3 cubed is 27, right? And it's already gone. 4 to the 4, yeah, 256, right? So there is no contest here. I mean, this function is absolutely, utterly insane in the growth department. This is 3,225, and then 6 to the 6, 46,656. So you get the idea of what happens, right? When x to the x shows up to a party. Like everyone else gets to sit down and shut up. Now, if I mix and match these functions, this means that the limit x goes to infinity of 1,000 raised to 1 million x divided by x to the x is equal to 0. I don't care how many zeros and whatever you have on top. I just don't care. Once this bad boy catches up, game over. So it is not what numbers you have. It is what are the functions that you are comparing. When I say that x to the x is the boss, everything prior to that, even the exponential function, is considered slower. So I call this slow over fast. I will never call exponential function slow if the big boy is not around. Never. Because obviously right? This function is faster than all the other ones, right? All of the polynomials and so on. So this is slow and fast is actually relative to each other, not relative to some external point of measurement. So as I said, if the big boy shows up, everything else is considered slow, including the exponential function. And you can have millions inside the exponential function, it's still irrelevant. Because once the big boy catches up, and catching up fast, look at that. I mean, come on, right? That's thousands off. All right, so time to put the growth rate, and so growth, so growth rate, it's like a theorem that ranks them. So what is the growth rates ranking? So what's the slowest? ln's. And you can raise them to whatever power you want. So if you have ln squared, ln to the million, whatever, that's going to be your slowest in comparison to linear comparison to anything else. Because remember, ln kind of bends like this and goes, right? Put just y equal x. Look what the linear y equal x does to y equal ln x. It's like there's no comparison. Just a basic x absolutely destroys ln. The next one is your square root of x. The square root of x is going to do this. Whoop. Still, just a basic y equal x is destroying a square root function. So those are the slowest ones, right? The ln's and the root x's are the slowest. And then, and we put these, this is kind of weird notation, you haven't seen this before. It just means slower rising, definitely less than, eventually less than, and so on. And then you have your polynomials. X squared, x cubed, blah, blah, blah. That's going to be rising slower than if you multiply this times this, which should be kind of common sense, so I'm not going to include it. But the next creature here is your exponential function, and then the big boss at the end. So no matter what you pick, it's going to be slow to the left, fast to the right, no matter where you are. Clearly, if you pick the big boy at the end, everything else is slower than it, right? And then you're just going to ask, oh, is the big boy in the numerator or denominator? Because if it's a numerator, it's infinity. If it's in denominator, it's 0. Because we have those, right? Slow over fast gives 0, and fast over slow gives infinity. Not a major talking point for Calc 1, right? Could save you 16 seconds of work somewhere, but an insane boost to your performance in Calc 2, and we are going to improve on it. I think when we do ratio test, is it ratio? I don't want to look for it now, but whatever. We're gonna add one more. We're gonna squeeze one more right here in between. But that's it. That's your L'Hopitals rule, guys. I hope you will study all of the cases. Try a whole bunch of homework examples, even though only 5 are required. Clearly, you can't learn this with 5 examples when you have so many cases and problems. Looking forward to see you do minimum like 20-30 problems here. Also, right, you have seen that this is something that you will use extensively in Calc 2. So if you're going to Calc 2, obviously, it should not be, it definitely has to be something that you know in order to be able to perform in Calc 2 class. We'll take a 5-minute break. When we come back, we have a very short section on what is called Newton's method, which would be a numerical way to find zeros of functions. So, yeah, I'll see you soon.